What if I told you that right now, at this very second, something built before the first personal computer is still talking to Earth, from a place no human has ever reached? That sounds almost impossible. Yet every message arriving today began its journey nearly a full day ago, traveling across billions of miles of empty space before reaching the giant antennas waiting on Earth. By the time scientists receive that signal, the spacecraft that sent it has already disappeared millions of miles farther into the unknown. But here's the first twist. For decades, most people believed Voyager 1's greatest achievements were already behind it. After all, it had explored Jupiter, Saturn, and captured some of the most iconic images in space history. It seemed like the mission had already completed its purpose. Then everything changed. Instead of fading into history, Voyager crossed a boundary no active spacecraft had ever crossed before, transforming from a planetary explorer into humanity's only direct observer of interstellar space. Suddenly, a mission expected to last just a few years became the only machine capable of answering questions no telescope on Earth could. And then came another surprise. Just as Voyager began sending some of the most valuable scientific data of its entire mission, NASA discovered an unavoidable problem. The spacecraft wasn't failing because of distance. It was slowly running out of the one thing no engineer could replace: power. Now, every transmission could be one step closer to the final message humanity will ever receive from the edge of the solar system. And the race to keep Voyager alive has become one of the most extraordinary engineering stories ever told. For almost 50 years, Voyager 1 has been doing something that sounds almost impossible. Every day, it sends a faint signal across billions of miles of empty space, carrying fresh scientific data from a region no other active spacecraft has ever explored. By the time that signal reaches Earth, nearly 24 hours have passed, and Voyager has already traveled another million miles deeper into the darkness. That alone is extraordinary. But here's the first turning point. Most people assume Voyager is simply drifting through empty space, quietly repeating the same routine year after year. The reality is far more remarkable. Every transmission arriving today contains direct measurements from interstellar space, a place beyond the sun's protective bubble where the environment is completely different from anything inside our solar system. No telescope can collect this information. Right now, Voyager is humanity's only first-hand witness to this distant frontier. Then, the story takes another unexpected turn. You might think another spacecraft is already on its way to replace it. After all, space technology has advanced dramatically since 1977. Modern probes are faster, smarter, and far more powerful. Yet, despite all that progress, there isn't a single active mission that can take Voyager's place anytime soon. If its signal stops tomorrow, humanity will lose its only continuous source of direct data from interstellar space for years, possibly decades. And that changes everything. Suddenly, every message is no longer just another routine transmission. It becomes irreplaceable. But the biggest surprise isn't the distance, it's time. Voyager wasn't built to survive this long. Engineers originally expected the mission to last only a few years. Instead, it has continued operating for nearly half a century using technology designed before the internet, smartphones, or even personal computers became part of everyday life. Every day it remains alive is another victory against expectations. Yet behind the scenes, NASA knows something the public rarely thinks about. The spacecraft isn't fighting the cold, or the distance, or even the harsh conditions of deep space. It's fighting its own clock. And to understand why Voyager is still alive today, we have to go back to 1977. When a mission designed for just a handful of years accidentally became one of the greatest engineering achievements in human history. On September 5th, 1977, Voyager 1 lifted off from Cape Canaveral with a mission that sounded ambitious for its time, but surprisingly modest by today's standards. NASA wasn't trying to build a spacecraft that would survive for half a century. The plan was simple: take advantage of a rare alignment of the outer planets, study Jupiter and Saturn up close, and complete the mission within just a few years. No one expected anything more. But then came the first turning point. That rare planetary alignment wasn't just convenient, it was a once-in-a-lifetime opportunity. By carefully flying past giant planets, Voyager could use their gravity like a giant slingshot, accelerating without burning extra fuel. Scientists realized this trajectory could send the spacecraft farther than any probe before it. At the time, it seemed like an incredible engineering success. Looking back, it was the decision that unknowingly set Voyager on a journey that would outlive generations of scientists. Then, another surprise emerged. When people compare Voyager to modern technology, they often assume it must have been upgraded over the years. It wasn't. The spacecraft still relies on hardware designed in the early 1970s. In fact, the phone in your pocket contains vastly more computing power than Voyager 1. Yet while smartphones are replaced every few years, Voyager has continued operating for decades in one of the harshest environments imaginable, where no repairs, software patches, or rescue missions are possible. That wasn't luck. It was the result of an engineering philosophy that seems almost old-fashioned today. build fewer systems, make them incredibly reliable, and eliminate every unnecessary risk. Every circuit, every instrument, and every backup system was designed with one goal: to survive when help would never come. But the biggest twist was still years away. After Voyager completed its historic encounters with Jupiter and Saturn, many believed the mission had reached its natural conclusion. NASA had achieved every major objective it originally set out to accomplish. For almost any other spacecraft, that would have been the end. Instead, it became the moment Voyager's greatest adventure quietly began. Because once the planets were behind it, the spacecraft started heading toward a destination no mission had ever reached. A place where entirely new discoveries were waiting, and where everything scientists thought they knew would soon be put to the test. Voyager 1's first destination was Jupiter, a planet astronomers had been studying for centuries. By 1979, scientists believed they already had a solid understanding of the giant world. Powerful telescopes had mapped its colorful cloud bands, tracked the Great Red Spot, and revealed its largest moons. They expected better pictures. They weren't expecting a scientific revolution. Then came the first turning point. As Voyager closed in, it began sending back images unlike anything ever seen before. The closer it got, the more Jupiter seemed alive. Violent storms stretched across the planet, lightning flashed through its thick atmosphere, and enormous cloud systems behaved in ways scientists hadn't predicted. Instead of confirming old theories, every transmission raised new questions. But Jupiter itself wasn't the biggest surprise. One of its moons completely stole the mission. That's when everything changed again. A tiny moon named Io had always appeared quiet through Earth's telescopes. Yet Voyager's cameras revealed towering volcanic eruptions, blasting material hundreds of miles into space. It became the first time humanity had directly observed active volcanoes on another world. The discovery stunned planetary scientists. Until then, many believed small moons gradually cooled down and became geologically dead. Io proved the opposite. Jupiter's immense gravity was constantly squeezing and stretching the moon, generating enough internal heat to keep hundreds of volcanoes active. Overnight, scientists had to rethink how entire planetary systems evolve. And just when it seemed Voyager had already made history, another breakthrough arrived. The third turning point came at Saturn. For centuries, Saturn's rings had looked smooth and elegant through telescopes, but Voyager's close-up images exposed something far more complex. Thousands of delicate ringlets, mysterious gaps, twisting patterns, and structures shaped by invisible gravitational forces. Meanwhile, its observations of Titan confirmed that the moon possessed a dense, nitrogen-rich atmosphere, unlike any other moon known at the time, making it one of the most intriguing places in the solar system. By every measure, Voyager had exceeded NASA's expectations. The mission had photographed 2 giant planets, rewritten textbooks, and delivered discoveries that scientists would study for decades. From NASA's perspective, the mission was complete. But what happened next would become the greatest surprise of Voyager's entire journey. Instead of shutting down after achieving its objectives, the spacecraft kept traveling toward a destination no probe had ever reached. Without anyone realizing it at the time, Voyager's most important discoveries were still waiting billions of miles ahead. By the time Voyager 1 completed its historic flyby of Saturn, its cameras had already captured thousands of extraordinary images. From NASA's perspective, there was little reason to keep taking photographs. The spacecraft was leaving the planets behind, and every remaining watt of electricity would become increasingly valuable. The logical decision was simple: turn the cameras off forever. But then came the first turning point. Astronomer Carl Sagan proposed one final idea before the cameras were retired. Instead of looking farther into space, why not turn Voyager around and ask it to look back at the place it had come from? It sounded like a simple request, but it created years of debate. Pointing the cameras toward the inner solar system meant aiming dangerously close to the sun. Engineers worried that intense sunlight could permanently damage the imaging system. Others argued that risking a healthy spacecraft for one symbolic photograph simply wasn't worth it. The proposal remained uncertain for years. Then, in early 1990, NASA finally approved the maneuver. That decision changed history. The second turning point came the moment Voyager slowly rotated and pointed its cameras back across billions of miles of space. Instead of finding a bright, detailed Earth, the cameras captured something almost impossible to believe. Our entire planet appeared as a tiny, pale dot suspended inside a thin beam of scattered sunlight. Everything humanity had ever built, every nation, every city, every discovery, every war, every dream, existed on a speck so small it occupied less than a single pixel. The image instantly became one of the most influential photographs ever taken. Not because it showed Earth in detail, but because it completely changed how we see our place in the universe. Yet the story has one final twist. The third turning point is that this iconic photograph almost never existed. Moments after completing the imaging sequence, Voyager's cameras were permanently shut down to conserve power. They have never been switched on again. Had NASA delayed the decision even slightly, or rejected Sagan's proposal altogether, the famous pale blue dot would never have been captured. Ironically, ending Voyager's photography didn't mark the end of its mission. It marked the beginning of something far more important. With its cameras now silent, Voyager turned its attention to an invisible frontier beyond the planets, a place no human-made object had ever entered. And what it discovered there would redefine where the solar system truly ends. For years, people assumed Voyager 1 was simply drifting farther away from the planets, heading into an endless stretch of empty space. But scientists knew there was one final destination still ahead, an invisible boundary that no spacecraft had ever crossed. The challenge was that no one knew exactly where that boundary was. Unlike a country's border or shoreline, the edge of the solar system has no sign announcing you've arrived. Instead, it is defined by something invisible, the point where the sun's influence finally gives way to the forces of the rest of the galaxy. Then came the first turning point. As Voyager traveled farther from the sun, its instruments began detecting subtle changes in the surrounding environment. The solar wind, charged particles flowing outward from the sun, was weakening. At the same time, high-energy cosmic rays from outside the solar system were becoming stronger. Scientists realized they were approaching a region no spacecraft had ever explored directly. But there was one problem. The evidence didn't agree. Some instruments suggested Voyager had already crossed into interstellar space, while others seemed to indicate it was still inside the sun's protective bubble. For months, researchers debated the data, and no one could confidently say where humanity's most distant spacecraft actually was. Then everything changed. The second turning point arrived in 2012, when Voyager detected a dramatic increase in plasma density. A signature, scientists had predicted, would exist only beyond the heliosphere. Combined with other measurements, the evidence became impossible to ignore. Voyager 1 had officially entered interstellar space. For the first time in history, a machine built on Earth was no longer exploring the solar system. It was exploring the space between the stars. That achievement alone would have secured Voyager's place in history. But the biggest surprise came afterward. The third turning point was that crossing into interstellar space didn't end the mission. It made it more valuable than ever. Every new transmission suddenly became something humanity had never possessed before. Direct scientific measurements from an environment no telescope could sample, and no other active spacecraft could reach. Voyager was no longer just surviving beyond its original mission. It had become humanity's only eyewitness in one of the least understood regions of our galaxy. And just as scientists began receiving the most unique data of the mission, another reality became impossible to ignore. The spacecraft still had working instruments, it still had a functioning transmitter. But it was slowly losing the one resource that could never be restored, its electrical power. Most people assume the greatest threat to Voyager 1 is the crushing distance between it and Earth. After all, it's traveling through one of the harshest environments imaginable, billions of miles from the nearest human. But that isn't what's putting the mission at risk. The real danger has been on board since the day Voyager launched. Then comes the first turning point. Unlike spacecraft orbiting Earth or Mars, Voyager can't rely on solar panels. At its current distance, sunlight is simply too weak to generate usable electricity. Instead, it depends on a radioisotope thermoelectric generator, or RTG, which converts heat from the natural decay of plutonium into electrical power. That system has performed far beyond expectations, keeping Voyager alive for nearly 5 decades. But physics has one rule that even NASA can't overcome. Every year, the plutonium produces a little less heat, which means Voyager loses a small amount of electrical power. The decline is gradual, only a few watts annually, but for a spacecraft operating on its final energy reserves, those few watts can determine whether an entire scientific instrument survives or is switched off forever. Then, the situation became even more difficult. The second turning point wasn't caused by a hardware failure, it was caused by a painful decision. Rather than waiting for Voyager to shut down unexpectedly, NASA began turning off perfectly healthy systems on purpose. Instruments that had operated successfully for decades weren't failing. They were being sacrificed to preserve power for the experiments that could still reveal new discoveries in interstellar space. Imagine owning the only telescope capable of seeing something no one else can, and being forced to remove one lens at a time just to keep it operating. That's exactly what mission controllers have been doing. Each shutdown extends the mission, but also brings it one step closer to its inevitable end. Then came the biggest realization of all. The third turning point is that today, Voyager isn't limited by science. It still has questions to answer. It still has instruments capable of making discoveries. The only thing standing between humanity and more knowledge is electricity. That has transformed every remaining watt into something priceless. And instead of accepting the countdown, NASA's engineers decided to attempt something few believed was possible, rewriting the rules for a spacecraft built nearly 50 years ago in a final effort to keep humanity's most distant explorer alive just a little longer. For most space missions, running out of power means one thing: the countdown has begun. Engineers monitor the spacecraft, collect as much science as possible, and prepare for the inevitable end. But Voyager 1 has never been an ordinary mission. Instead of accepting its fate, NASA's engineers asked a different question. What if there was still a way to buy more time? That question led to one of the boldest engineering efforts in the mission's history. The first turning point was realizing that Voyager didn't necessarily need more power. It simply needed to use the remaining power more efficiently. After decades in deep space, mission engineers began carefully studying every electrical system on board. Some components consumed valuable energy, even though they were no longer essential for Voyager's current mission. If those systems could be reconfigured or reduced, the spacecraft might continue operating its most important scientific instruments for months or even years longer than expected. It sounded promising, but there was a serious catch. Every command sent to Voyager travels for nearly 24 hours before reaching the spacecraft. Another full day passes before engineers receive a response. If something went wrong, there would be no way to react instantly, no emergency shutdown, and no second chance. Every adjustment became a gamble played across billions of miles. Then the stakes grew even higher. The second turning point came when engineers realized they weren't just protecting an aging spacecraft, they were protecting humanity's only active laboratory in interstellar space. A single mistake could permanently disable instruments that no other mission could replace. That meant every command was reviewed, simulated, and tested repeatedly before it was ever transmitted. Sometimes, the smallest software change required weeks of planning because one unexpected reaction could end a mission that had survived for nearly half a century. Then came the most remarkable twist. The third turning point wasn't that every experiment succeeded, it was that Voyager kept proving everyone wrong. Time after time, the spacecraft responded to carefully planned adjustments, continuing to send valuable data long after experts believed its operational life was nearing an end. Each successful improvement didn't just extend the mission, it demonstrated the incredible foresight of the engineers who built Voyager decades earlier. But keeping the spacecraft alive solved only half the problem. Even if Voyager continued transmitting, there was another extraordinary challenge. How do you hear a signal so unimaginably weak that by the time it reaches Earth, it's barely distinguishable from the background noise of the universe itself? Keeping Voyager 1 alive is an extraordinary challenge, but keeping in contact with it may be even more remarkable. Right now, every piece of scientific data Voyager sends begins as an incredibly weak radio signal traveling across billions of miles of empty space. It moves at the speed of light, yet even then, it takes nearly an entire day to reach Earth. By the time mission controllers receive a single transmission, Voyager has already traveled another 1,000,000 miles into interstellar space. Then comes the first turning point. Most people imagine Voyager sending a powerful signal back to Earth. The reality is almost unbelievable. Its transmitter produces only a tiny amount of power, less than many household light bulbs. As that signal spreads across billions of miles, it becomes unimaginably faint. By the time it reaches Earth, it's so weak that detecting it is like trying to hear a whisper from the other side of a continent while standing in the middle of a hurricane. And yet, somehow, scientists still hear it. The reason is one of NASA's greatest engineering achievements. The Deep Space Network, a global system of giant radio antennas, continuously listens for signals from humanity's most distant spacecraft. These massive dishes are so sensitive that they can detect Voyager's faint transmission even after it has crossed the vast emptiness between the stars. But then another challenge appeared. The second turning point came when parts of the Deep Space Network required major upgrades and maintenance. During those periods, communication opportunities became limited, reminding engineers just how fragile this connection really is. It wasn't Voyager that was in danger of going silent. It was Earth's ability to listen. For the first time, scientists realized the mission depends on two extraordinary machines working perfectly together, one traveling alone through interstellar space, and another spread across our entire planet. Then comes the final twist. The third turning point is that one day the signal won't disappear because Voyager is destroyed. It will simply become too weak to hear. The spacecraft may continue traveling through the Milky Way for millions of years, perfectly intact, while Earth hears nothing but silence. Humanity won't witness an explosion or a dramatic ending. We'll simply stop hearing the oldest explorer we've ever built. But even after the final radio transmission fades forever, Voyager will still carry something that could outlive every signal it has ever sent. A message intended not for us, but for whoever or whatever might one day find it among the stars. Every great mission eventually reaches a moment when no engineering breakthrough, no clever solution, and no careful planning can overcome the laws of physics. Voyager 1 is approaching that moment. Yet what makes its story extraordinary isn't how it will end. It's how completely it exceeded every expectation. The first turning point is realizing that Voyager never actually failed. It accomplished every objective NASA gave it decades ago. It explored Jupiter and Saturn, transformed planetary science, captured some of the most iconic images in history, and then achieved something no one had imagined possible by becoming the first human-made object to enter interstellar space. Everything that happened after its original mission ended has been an unexpected bonus for humanity. Then comes the second and perhaps most surprising realization. One day, engineers will point the deep space network toward Voyager's familiar location in the sky, and nothing will come back. There won't be a dramatic countdown, no final goodbye, no emotional last message, just silence. Not because Voyager was destroyed, but because its remaining power will no longer be enough to send a detectable signal across billions of miles of space. The conversation between Earth and its most distant explorer will simply come to an end. But that isn't the end of Voyager's journey, it's only the end of our ability to hear it. And here's the final turning point. Long after its instruments stop working, long after its transmitter falls silent, and long after everyone alive today is gone, Voyager 1 will continue its endless voyage through the Milky Way. Attached to its side, the Golden Record will still carry the sounds, music, languages, and images of Earth, a silent introduction from a civilization that dared to explore beyond its own world. Perhaps that's Voyager's greatest legacy. It didn't just expand the boundaries of science, it expanded the boundaries of what humanity believed was possible. Right now, somewhere in the darkness between the stars, Voyager 1 is still moving forward. It's still carrying our story, and for now, it's still whispering back to the world that created it.